Once more, instructor Carlos Plain of Durham School states, absolutely. I went through my whole time on Earth engaging an unequivocal hypothesis of the universe. At last, the hypothesis is being attempted. I welcome that, since that is the way we push ahead. That is the manner by which we make strides in science. The James Webb Space Telescope is disrupting a significant portion of what has been considered truth in cosmology. For the new year, another ultra-deep image shows that we have serious errors in cosmology. The telescope, which ought to show us the major stars of the universe, is turning into a challenge to past perspectives and may present us with a completely revolutionary science. Not all experts are responding with fear to these new realities. Some well-informed experts welcome the changes, as it has long been evident that something was amiss with our old hypothesis. The discrepancy in the evaluation of the universe's expansion speed alone should have shaken experts' perceptions already. Yet, rather than resolving these issues, they adhered to outdated hypotheses. The cosmic microwave background radiation, CMB, considered the oldest light in the universe, was created around 380,000 years after the Big Bang, when the universe had cooled enough for electrons and protons to form stable hydrogen atoms. Scientists call this process reionization, which made the universe transparent to light. The CMB was first observed in 1964 by American physicists Arno Penzias and Robert Wilson while they were working on a new type of radio antenna. This discovery was, for a long time, considered one of the strongest pieces of evidence for the Big Bang hypothesis, earning Penzias and Wilson a Nobel Prize and a permanent place in the history of space science. The CMB likely offers a glimpse into the early universe, with small temperature differences providing crucial data about conditions shortly after the Big Bang. Scholars use the CMB as a robust foundation for fundamental estimates of the material universe, including its expansion rate. Cosmologist Edwin Hubble had already established in the late 1920s that distant galaxies are receding from us at speeds proportional to their distances. Today, this observation is known as the Hubble law or Hubble constant. Hubble didn't have the advanced measuring techniques available decades later when the CMB was discovered, leading to a recalculated expansion rate. These new measurements were generally lower than Hubble's original estimate. Later, scientists recalculated the rate using Type Ia supernovae as standard candles, which produced stable light that could be used as reliable measuring points. The CMB yielded an expansion speed of around 67 kilometers per second per megaparsec, while estimates using cosmic bursts yielded around 74 kilometers per second per megaparsec. What does this error in the universe's expansion rate really tell us? Did you realize that this discrepancy has been known since the 1990s? Since that time, researchers have suspected that something might be wrong with the assessment of the CMB, the measurement methods, or the very nature of the universe's expansion. This difference between the observed and predicted values of the expansion rate is referred to in science as the Hubble tension. The implications of this tension are profound, suggesting that key aspects of how we understand the universe might be flawed. For years, scientists were puzzled. Since the James Webb Space Telescope became operational, it has provided researchers with stunning data that may now shed light on the issue of the universe's expansion speed. It has observed systems so old and mature that their development should have started before the Big Bang, according to current theories. These revelations are shaking the foundations of old cosmology. Researchers no longer talk about mistakes or errors in measurement. They speak of a crisis in modern astronomy. Not only might the expansion rate be wrong, but the entire concept of expansion, or even the Big Bang itself, is being questioned. Images from the telescope provide evidence of a universe vastly different from what we have long believed. The Hubble tension was the first warning to scientists who still cling to old theories. Now they face a dilemma. Do we truly understand the universe? Many experts are wrestling with this crisis. They examine space with a mix of wonder and fear, grappling with what they observe. In light of the crisis in science, we must ask ourselves, what do we truly know about the universe? To answer this, we need to understand how science functions. Theoretical scientists use a complex system of mathematical models, precise data, and insightful reasoning to draw conclusions. Their understanding arises from a combination of observations, measurable phenomena, and theoretical interpretations. The term theory itself indicates that these are constructs and ideas, not absolute truths. The most reliable data we have come from telescope images, sound waves, and radiation collected with radio telescopes, as well as the latest findings from neutrino detectors or gravitational wave observatories. With the James Webb Space Telescope, we now have an instrument that can split light into individual frequencies and analyze it in unprecedented ways. Webb can show us the composition of galaxies in the early universe, billions of years ago, their mass, the number of stars present, and the trajectory of their evolution. However, Webb has its limitations. For instance, it cannot always fully distinguish between galaxies and black holes with massive gravitational forces that emit light as brightly as galaxies. We must face the reality that our science has long accepted too many probabilities as facts while dismissing alternative explanations. For years, research has been overly confident in its precision. The latest discoveries from the James Webb Space Telescope are vital clues, prompting us to replace old theories with new insights, as has often happened in science. Scientists eagerly anticipate new discoveries, which are both astonishing and transformative. Many researchers are striving to develop new explanations. These discoveries shake the foundations of modern science, alarming many experts. The current models of modern science are still largely based on Isaac Newton's laws from the 17th century. His laws of motion and universal gravitation provided the framework for understanding the physical universe for centuries. However, as science has progressed, new discoveries, such as Einstein's theory of relativity and quantum mechanics, have challenged and expanded Newtonian principles. Now, the James Webb Space Telescope is adding another layer of complexity to our understanding. The data it provides suggests that we may need to rethink not just the details of our models, but the very foundations upon which they are built. For example, the idea of a singular Big Bang event as the definitive beginning of the universe is being questioned. Could there have been multiple bangs? Or might the universe operate within a cyclical model where expansion and contraction alternate in an eternal rhythm? These questions are not just academic exercises. They challenge the very fabric of our understanding. If the universe does indeed follow a cyclical model, where periods of expansion and contraction alternate, then the Big Bang might not represent a singular creation event, but rather one phase in an endless cosmic cycle. Such a perspective would require a complete overhaul of existing cosmological models, reshaping our understanding of time, space, and the origins of matter. The James Webb Space Telescope has also raised questions about the maturity of ancient galaxies. Observations have revealed galaxies so massive, structured, and evolved that their existence shortly after the Big Bang defies current models. According to established theories, there should not have been enough time for such systems to form. This impossible early galaxy problem suggests that either our understanding of galaxy formation is incomplete or the timelines of the universe's history need adjustment. The implications are profound. If galaxies formed earlier than expected, it might point to new physics or unknown processes that shaped the early universe. Moreover, the telescope's ability to analyze the chemical composition of these ancient galaxies has revealed surprising results. Elements like carbon, oxygen, and nitrogen, produced in the cores of stars and distributed through supernova explosions, are present in quantities that suggest star formation and evolution happened much faster than predicted. Some researchers propose that the universe's first stars, often referred to as population 3 stars, might have been far more massive and short-lived than previously thought. These stars could have quickly synthesized heavier elements, accelerating galaxy formation. However, direct evidence of population 3 stars remains elusive. The tension between observation and theory extends beyond galaxies. The telescope's detailed data on the distribution of dark matter and dark energy further complicates the picture. Dark matter, the mysterious substance thought to constitute about 27% of the universe, and dark energy, the force driving the universe's accelerated expansion, remain poorly understood. New observations suggest that the behavior of dark matter and dark energy might not align with current models. For instance, the distribution of dark matter in ancient galaxies challenges simulations based on the standard model of cosmology. Similarly, The role of dark energy in the universe's expansion might require reevaluation in light of Webb's findings. These anomalies underscore a growing realization. Our current understanding of the universe is, at best, an approximation. The scientific method thrives on such moments of crisis. When data contradicts theory, it signals the need for new ideas, models, and experiments. As we move forward, the James Webb Space Telescope serves as both a tool and a symbol of scientific progress. It invites us to question long-held assumptions, embrace uncertainty, and explore the cosmos with humility and curiosity. The challenges posed by its discoveries are daunting, but they also represent an opportunity to advance our understanding of the universe. As history has shown, scientific revolutions often emerge from the tension between what we expect to find and what we actually observe. The questions raised by Webb's data about the origins of galaxies, the nature of dark matter and energy, and the very structure of the universe may lead to a new era in cosmology. This journey will require collaboration across disciplines, innovative technologies, and an openness to rethinking the foundations of physics and astronomy. In the end, the ultimate goal remains unchanged: to understand the universe and our place within it. As we look to the stars, guided by tools like the James Webb Space Telescope, we are reminded of the enduring power of human curiosity and the boundless potential of discovery. Rhythm. These ideas were once relegated to speculative theories, but the evidence now compels scientists to consider them seriously. Moreover, the role of dark matter and dark energy, concepts introduced to account for observations that cannot be explained by visible matter and energy, is being re-examined. Some researchers argue that these constructs might be placeholders for phenomena we have yet to comprehend. The crisis in modern cosmology is not just a challenge, it is an opportunity. It pushes scientists to think beyond established paradigms, to explore new models that might better fit the data. History has shown that such periods of upheaval often lead to groundbreaking advancements in our understanding of the universe. For example, the discovery of the cosmic microwave background radiation fundamentally shifted our perspective on the origins of the universe. Similarly, the revelations provided by the James Webb Space Telescope may pave the way for a new era in cosmology, one that reconciles the inconsistencies of the past and offers a more cohesive narrative of the universe's evolution. In the meantime, debates within the scientific community are likely to intensify. Questions about the universe's age, its rate of expansion, and the nature of its earliest structures are at the forefront of ongoing research. While some experts hold steadfast to traditional models, others embrace the uncertainty, seeing it as a chance to uncover deeper truths. In the words of teacher Carlos Planck, that is how we push ahead, that is how we gain ground in science. It is through questioning, testing, and sometimes overturning what we thought we knew that progress is made. The James Webb Space Telescope reminds us of the vastness of what we have yet to discover and the necessity of remaining open to new possibilities, no matter how disruptive they may seem. As we venture further into this uncharted territory, one thing is certain: the universe still holds countless secrets, and our quest to understand it has only just begun. Movement and gravity were the groundwork of our perception of the truth of this world and the universe for quite a while. Newton's principles explained the movement of objects under normal conditions and functioned particularly well on Earth. However, in space, his theories required advancements, which were mostly completed by Albert Einstein in the mid-20th century. Einstein's special theory of relativity, published in 1905, changed how we interpret reality, showing that space and time are relative to each other and depend on the observer's motion. His general theory of relativity, published in 1915, expanded this idea with mathematical representations of gravitational effects based on the curvature of space-time caused by masses, such as stars or galaxies. Einstein's principles and insights were significant in many areas, yet he also recognized their limitations. He knew his theory would never fully describe the universe and yearned to discover a unified theory, which he never achieved. To this day, no other expert has reached this stage either. Wouldn't it be fascinating to know where the solution lies? Michio Kaku, a prominent astrophysicist from the USA, mentioned in an interview that resolving this issue would undoubtedly earn a Nobel Prize. Could we investigate whether the experts have overlooked potential misinterpretations or whether our telescopes are to blame? Dark matter and dark energy are at the top of the suspect list for the major causes of the cosmological crisis. Our evolving models of the universe suggest that dark matter and dark energy make up around 95% of the universe. However, neither has been directly observed, and their confirmed existence has never been demonstrated. They likely exist in a form or property we do not yet understand, requiring alternative explanations for the universe's expansion and the dynamics of galaxies. On the other hand, their properties might have evolved over time, suggesting a form of progression. Gravity is another theory that must be revisited. This force, which creates attraction through mass or space-time curvature, has not been fully explained. The concepts of space-time curvature, originating from Einstein and later supported by modern physics, may need to be reconsidered. We cannot dismiss the possibility that gravity has unexpected properties or that another force is responsible for gravitational attraction between objects over time. A few constants have been established in cosmology and astronomy as universal principles. The study of the universe has always been a journey defined by our constant pursuit of understanding and discovery. From ancient civilizations observing the stars to modern space telescopes exploring the depths of the universe, every step toward advancement and theory has uncovered new mysteries while challenging established beliefs. In the field of cosmology, the James Webb Space Telescope, JWST, stands as a beacon of scientific progress, promising to revolutionize how we interpret the universe's origins and evolution. Launched with unprecedented capabilities, JWST represents a leap forward in observational astronomy. It is designed to look deeper into the universe than ever before, with extraordinary precision in studying radiation. The cosmic microwave background, CMB, often referred to as the afterglow of the Big Bang, provides a glimpse of the universe as it existed just moments after its first interaction with matter. This ancient form of radiation carries essential information about the universe's initial conditions, including temperature variations crucial to understanding the evolution of galaxies and large-scale structures. The ongoing debate over the potential values of the Hubble constant, known as the Hubble tension, suggests that something may be wrong with our fundamental understanding of the universe's initial conditions. These discoveries challenge traditional theories and demand a reassessment of whether our perspective on cosmic evolution is fundamentally flawed. New insights might reveal hidden aspects of the universe's creation, raising questions about dark matter and dark energy, two unexplained components that comprise most of reality. The progress of science relies on our ability to reshape theories based on new data. Webb's mission exemplifies this pursuit. Its discoveries will serve as a foundation for future cosmological discussions, igniting new perspectives on the universe's mysteries. The future of cosmology may witness tremendous shifts, leading to profound implications for how we interpret the universe. From the Big Bang to the ongoing processes that define its fate, the answers to the greatest questions may lie beyond our current knowledge. Webb's observations may ultimately be essential in uncovering new insights that could reshape how we understand reality itself. The path forward for cosmology and space science is filled with potential. Each groundbreaking observation and piece of data from telescopes like Webb brings us closer to answering the most profound questions humanity has ever posed. How did the universe begin? What is its ultimate fate? Are there other forms of life out there, or are we alone in this vast cosmos? These questions may one day find answers, and the James Webb Space Telescope is at the forefront of this monumental effort. The future of cosmology will likely involve a combination of new technologies, refined theories, and groundbreaking discoveries that continue to push the boundaries of what we know. As we embark on this ongoing journey, the interplay between technology, theory, and experimentation will continue to shape our understanding of the cosmos. The questions we seek to answer are not only about the past, but also the present and future. What lies beyond the observable universe? Could there be other dimensions? Or are we truly alone in this vast space? The tools at our disposal, like the James Webb Space Telescope, provide us with the unprecedented ability to peer deeper into the universe and trace its origins more clearly than ever before. Every new discovery challenges us to rethink everything we thought we knew about reality. Moreover, the scientific community's willingness to question and explore even the most established theories is essential in pushing the boundaries of knowledge. Just as past discoveries such as the heliocentric model, the theory of relativity, and quantum mechanics radically shifted our understanding of the universe, future breakthroughs could provide answers to the most profound mysteries of existence. However, the path forward is not without its challenges. As new data is collected, it often raises as many questions as it answers, requiring a continual process of refinement and recalibration of our models. Yet, this is the essence of science, the constant pursuit of truth, even when the answers are elusive. One of the most exciting aspects of our current scientific endeavors is the convergence of various fields, cosmology, physics, and even philosophy. The boundaries between these disciplines are becoming increasingly fluid as researchers seek to understand the fundamental nature of reality. Concepts like dark matter and dark energy, once thought of as separate from mainstream physics, are now key components of our understanding of the universe's structure and evolution. It is this blending of ideas and perspectives that will likely lead to the next great breakthroughs in science. The exploration of space is no longer confined to theoretical frameworks. With space telescopes like Webb, satellites, and future space missions, humanity is taking a hands-on approach to unraveling the mysteries of the cosmos. These technologies offer a tangible connection to the universe, bringing us closer to understanding its origins, its workings, and, ultimately, our place within it. As we advance in our quest for knowledge, we may find that the universe is far more complex, interconnected, and dynamic than we can currently imagine. The next phase of cosmological research will undoubtedly uncover surprises that challenge our preconceptions and open up new avenues of exploration. Just as previous generations of scientists stood on the shoulders of those who came before them, future generations will benefit from the discoveries and insights we make today. In the end, the universe is vast and filled with secrets yet to be discovered. Our curiosity and drive to explore, to understand, and to know are what propel us forward. Whether through space telescopes, new theories, or groundbreaking experiments, the pursuit of knowledge remains at the heart of our existence. The future of cosmology, like the universe itself, is limitless, waiting to be explored, understood, and appreciated.